It's my pleasure to introduce Elena Amato. Thank you so much for giving us this talk today at the CDY Institute. Elena is an expert on several areas of theoretical high energy astrophysics. She's worked on a variety of interesting problems, including acceleration and transport of relativistic particles, physics of relativistic plasmas, cosmic rays, supernova remnants, and pulsar wind nebulae. Currently, Elena is a professor at INAF, the Observatory Astrophysics in Firenze in Italy. And she's been there for some time. Her PhD was at the University of Florence in Italy. Title of her thesis was Particle Acceleration and Transport in Pulsar Wind Nebulae. Elena has had a variety of research positions at various places, including University of California, Berkeley, and she was also a visiting scientist for several times at Kavli Institute of Theoretical Physics at Santa Barbara in California. Elena also teaches high energy astrophysics and for both graduates and undergraduates at the University of Florence. And she's lectured on pulsar wind nebulae at several schools and summer schools and for graduate students as well. Her recent focus and her expertise is on the pulsar wind nebula and particularly the CRAB, and that's the title of her talk. The title of today's talk is the CRAB Pulsar Wind Nebula. So welcome, Elena. Thank you very much again. And I think the way we will structure this is we will start out with your talk, 50 minutes, so whatever time you need. And then we will have questions on your talk and invite everyone to either post it on the chat or just ask the question. And then what we've been doing with these CDY series is this is also an opportunity for people to just generally discuss on broader topics, and Felix will moderate that part of those last 30 minutes of it. So that's an opportunity to just talk and discuss in general the question, the subject of your talk, as well as broader topics. So feel free to jump in at that point. So with that, Elena, go ahead, please share your slide and let's get started.
Yes, thank you very much. Let me see if yes, am I sharing the right screen?
Yes, you are. And I'm just going to remind everyone that we are recording, and I'm going to request that if you're not speaking, please mute.
Okay, so thank you very much for this introduction, Rashmi. That sounded really like more than I am. So today I'm trying to review a bit recent and not so recent results about the CRAB Nebula, and of course the CRAB Nebula, as many of you will know, is the best studied object in the universe outside the solar system. These are Jeff Hester's words from 2008, and I think this is still true. So reviewing the physics of these objects is rather challenging, and I'll try to do my best. So the picture that you see here is the CRAB Nebula as imaged throughout the entire electromagnetic spectrum from radio to hard X-rays. We'll see in the talk that now we've got higher and higher energies for this object. And my slide, okay, I managed to switch slide. This is the CRAB Nebula spectrum. Aside from pictures, you've got spectral information. This has been imaged or measured by potentially, I think, every instrument that's been ever built for astrophysics. And what we observe is a very broad non-thermal spectrum. And yellow part here is interpreted as synchrotron radiation by relativistic particles gyrating in a magnetic field of order 100 microgauss. And the purple part is actually inverse Compton scattering with a local photon field that in this particular source not only includes the CMB and the general backgrounds, but also the synchrotron photon field is so strong that it has to be taken into account and serves as an important target for the inverse Compton radiation. The source of all these particles, of course, the particles are continuously burnt out by emitting radiation, and the source of these particles and of this enhanced magnetic field with respect to the ISM value was recognized to be a pulsar, a central pulsar, even before the discovery of pulsar. This was an initial suggestion by my PhD advisor, Franco Pacini, dating 1967, 1 year before the pulsar discovery. The Crab Nebula is the prototype of an entire class of supernova remnants that are called pulsar ring nebulae or Plarians. And these are described from the point of view of observations strictly as center field morphology SNRs with broad non-thermal spectra and a flat radius spectrum. Flat meaning that the spectral flux scales as nu to the minus alpha, with alpha less than 0.5, which to zeroth order is interpreted as emission of particles with a spectrum flatter than e to the minus 2. Okay, this is something that's going to be important during the talk. Now, the Crab has been recently, and even not so recently, say in the last 10 years, has been identified as the only well-established galactic pevatron. Now, this is the gamma ray spectrum, the gamma ray part of the Crab spectrum, and both here and here, what you're seeing is PV electrons. From the latest LAHAZO measurement, for which we see photons with energies of 1.1 PeV, we immediately deduce that if this is inverse Compton emission, and the only target for inverse Compton emission at this very high energy is left as the CMB, well, these electrons are 2.4 PeV electrons. Most of what I will say in this talk is actually written up in this recent paper, in this recent review that I published with Barbara Olmi as part of a special issue on gamma rays. Let's go back to the Crab, and let's start from the very beginning. So we said the source of all the emission is the central pulsar. The central pulsar is expected to somehow launch a wind. Particles are efficiently extracted from the star surface, certainly electrons, possibly also protons. Particles are extracted from the star surface, and they form a co-rotating magnetosphere that cannot extend forever. And at distances where the co-rotation is not possible, a wind starts. Okay, so this wind will be mostly formed by electrons and positrons, because for each electron extracted from the star surface, efficient pair production takes place in the magnetosphere. So it will be a pair wind with a magnetic field that will be mostly toroidal at the distances larger from the light cylinder radius that sets the outermost limit of the co-rotating magnetosphere. And there is a possibility that there are protons too. The total wind energy can be written in this way. So this is E dot, the total energy lost per unit time by the pulsar. This is kappa, the pair multiplicity, the number of pairs that are produced for every electron that leaves the star surface. This N dot GJ is the Goldrich and Julian charge loss rate, which only depends on the pulsar rotation frequency and the pulsar magnetic field. This gamma here is the wind Lorentz factor, the final wind Lorentz factor, far enough away from the light cylinder. And this ratio here stands for the possibility that ions, protons, or higher mass ions are part of the wind. Sigma instead is the ratio between Poynting flux and kinetic energy flux of the pairs in the wind. Okay, so these are all the ingredients that can go in the pulsar wind, and the sum of them all makes the total energy lost per unit time by the pulsar. What is known and what is unknown in this equation? Well, as we said, n.gj is well known. Mass ratio between ions and electrons, well, let's say MP over ME is well known. What is unknown is the permultiplicity of the pulsar magnetosphere. We have models for that, but it's not something that's certainly known. The wind-Lorentz factor, the terminal wind-Lorentz factor is not known, and the magnetization sigma is not known. These are the things that we are going to try and constrain in order to understand how the system works. What happens to the wind after it flies away from the pulsar? Well, the pulsar, in the case of the Crab Nebula, is surrounded by the supernova remnant from the debris of from the ejecta of the explosion that produced the pulsar. And so the system is rather complex. You have the outermost interesting thing is the forward shock that is expected to propagate in the ISM, and that's not seen in the case of the Crab Nebula. Then you've got the ejecta and a reverse shock propagating in the ejecta. Then there's the contact discontinuity between the ejecta and the pulsar material. And inside, instead, you've got the pulsar wind that starts out extremely relativistic, but has to slow down somewhere in order to match the condition of non-relativistic expansion imposed by the contact discontinuity with the ejecta. And the slowing down happens at a termination shock, which is this thing here. The position of the termination shock you can infer without knowing pretty much anything, meaning that it's just determined to zeroth order by pressure equilibrium between the run pressure in the wind and the pressure of the material that's been accumulating between the termination shock and the contact discontinuity, which is simply written as E dot times T divided by the volume. When you go and work out the numbers for the you immediately find that this relation here translates in this very simple expression here, which only depends on the ratio between the nebular expansion velocity and the speed of light, and gives a ratio between the termination shock radius and the nebular radius, which is of order square root of V nebula over C. When you go and look at the Crab Nebula, you see that that distance from the pulsar exactly corresponds to the boundary of the internal region of depressed emissivity, a dark inner region that's observed at all frequencies from radio to optical to X-rays. So it's, it's straightforward to interpret the portion of plasma inside this region as the cold, non-emitting wind. So the particle acceleration, the dissipation and the particle acceleration that then gives rise to the bright emission has to occur at the termination shock, okay? Because from there, the emission starts. At least most of the particle acceleration has to occur there. But what is the spectrum of particles that the termination shock is bound to produce? But well, when we model the nebular emission, what we deduce is the spectrum as the one that you see on the left. So flat spectrum at radio frequencies. So in general, for pulsar wind nebula, it will be between -1 and -1.5. In the case of the Crab Nebula, it's like -1.6 exactly. And a steeper spectrum for optical and X-ray emitting particles. The break here, the inner break, a break intrinsic to the particle distribution, has been for ages deduced to be at this kind of energy, around 500 GeV, say between 200 and 700, depending on the model, but around 500 GeV. Okay, so from just one zone modeling, the essential information one gets is that this object here accelerates, the termination shock or the nebula accelerates particles up to PeV energies, somehow sustains a magnetic field which on average is of order 100 microgauss, and more than 20% of the pulsar spin down energy is converted into radiation. So this is an extraordinary accelerator in all respects. Now, how does the acceleration work? What is that makes the particle acceleration so efficient in this place? Well, that shock that we were looking at is expected to be a collisionless shock. There is no way it cannot be it can be anything else than a collisionless shock. So the possibilities for dissipation and for particle acceleration depend essentially on three things: the composition of the flow, the magnetization of the flow, and the magnetic inclination. I think I'm not forgetting anything. Now, the only well-assessed parameter is the magnetic inclination. The pulsar wind is highly relativistic. The Lorentz factor is estimated to be between a few times 10 to the 3 in the lowest case, up to a few times 10 to the 7 in some other estimates. So the shock is extremely relativistic, so it has to be mostly perpendicular, just because in order for it not to behave as a perpendicular shock, the magnetic field should be aligned with the particle flow within 1/gamma, and gamma is this large number that I was mentioning. We need to constrain these other two parameters to understand what can be accelerating particles in the Krebs nebula. So how do we do this? Well, we do this by modeling the pulsar wind nebular plasma. The very first modeling, dynamical modeling, which was actually static modeling, started with Kennel and Coroniti in 1984. And basically, the assumption was that of a radial outflow. And with a radial outflow, one can immediately constrain the magnetization of the flow to be of order 3 times 10 to the minus 3. This is just based on relative sizes, basically, of the termination shock and of the contact discontinuity. In order for a wind to be confined within this cage, the magnetization had to be low enough. You can estimate it as Vn over c, expansion velocity of the nebula divided by c. And so it's just 3 times 10 to the minus 3. Very, very low. If you want to model the spectrum, which Kennel and Coroniti did, in order to reproduce the optical and X-ray emission, you also can infer the particle spectral index, 2.3, the wind Lorentz factor, 3 times 10 to the 6th, and the particle injection rate, 10 to the 38 particles per second. Okay, this is all that you can learn about the pulsar wind plasma if you are modeling it in 1D. Immediately, this posed a serious problem to solve, which is the so-called sigma problem. And the problem is as follows. From pulsar theory, at the light cylinder, the pulsar wind is expected to have a high magnetization. This is an electromagnetically driven wind. The electromagnetic energy component will be dominant at the light cylinder by far. How do you convert from sigma of order 10 to the 4 to sigma of order 10 to the minus 3 at the termination shock radius? Well, this was for a long time a tough mystery. I will not discuss models proposed to solve it, especially because this estimate here has now changed by quite a bit. And the change was induced by the beginning of the 2D, of the multi-D modeling of pulsar wind nebulae and of the Krebs nebula in particular, which was prompted by Chandra observations showing with this satellite excellent spatial resolution at X-ray energies, showing, I was saying, jets and tori everywhere. If you want to have a chance to reproduce a jet or a torus, you need to move to 1D. But even more interesting was the theoretical push to move to 2D. And the problem is that if the system was really behaving as a 1D system with a spherical shock, there was no way of explaining the appearance of a jet from very close to the pulsar, from a distance much closer to the pulsar than the inferred position of the termination shock in this plane. Okay, so the idea was one should abandon the 1D picture, the spherical shock picture, and move to something like this for the shock shape, with a shock much closer to the pulsar in what is inferred to be along what is inferred to be the pulsar rotation axis, and actually more elongated in the equatorial plane of the pulsar rotation. The kind of recipe that lets you move from this picture here to this picture here is you should take into account the anisotropy of the pulsar wind, the latitude dependence of the flux of energy that leaves the pulsar. There's something. Okay. Is it all okay? Can you hear me?
We can hear you. I think that we should ask people to mute. I think maybe somebody muted. Go ahead. Sorry for the interruption.
Okay. Oh no, sorry. Okay. So the energy flux in the pulsar wind is expected to scale based on magnetosphere modeling. Is expected to scale as sin squared theta. Where theta is the angle, measures the latitude starting from the equator, okay, from the pulsar rotational equator. As you see in this picture taken from Anatoly's work from 2006, basically you have that the toroidal magnetic field is expected in this case, which represents an aligned dipole, is expected to reverse its sign in the pulsar rotational equator. Now, if you are looking at an inclined rotator, as the crab is expected to be, and most pulsars are expected to be, otherwise they wouldn't pulse, you end up with a region with a current sheet extended in an equatorial region whose angular extent is determined by the inclination between the magnetic and rotation axis of the pulsar. In this equatorial current sheet, dissipation is possible, and the magnetic field overall is expected to tend to zero in the entire region, reaching zero in the equatorial plane of the pulsar rotation. So this is the kind of recipe one uses for the magnetic field. Energy flux scales as sin squared theta. Toroidal magnetic field scales as sine theta times a function that takes into account it's going to zero in the equatorial plane of the pulsar. When you input this in a 2D MHD code, you end up with a shock structure that looks like what you see in this picture here. So the white part is the unshocked wind, and here is the shock. You see that there are parts of the shock that are highly oblique, and this implies that there's mildly relativistic flow even behind the termination shock. And of course, this picture allows you to reproduce a very nice feature once you compute the X-ray emission on top of this MHD flow structure, you find as a result, mostly of Doppler boosting, all the nice feature that you see in objects like crab or theta. Now, what's interesting for us, though, is that moving from 1D to 2D changed the estimate of sigma quite a bit by an order of magnitude. In this picture here of the anisotropic wind with the oblate termination shock, what is making the collimation, what is solving the problem of making a jet, is actually the building up of hoop stresses in the nebula that managed to divert the equatorial flow towards higher latitudes. So basically, you can only get a jet if you reach equipartition somewhere in the nebula. You see here how the flow structure depends on sigma, and for very low magnetization, most of the energy flows in the equator. As you increase the magnetization and build up the Hooke stress in the nebula, you convey more and more of the flow along the polar axis, even too much if you increase sigma too much. All was good. I mean, very nice picture came out of this modeling, but the trouble was that when you went and checked in terms of spectrum whether the pretty picture were really described in the system, you would find that, well, no, this pretty picture didn't correspond to the Crab Nebula at all, because the inverse Compton flux was highly overestimated by an order of magnitude. This overestimate came from the fact that, in fact, the magnetic field in the simulations was of order 10 to the minus 5 Gauss, an order of magnitude lower than it should have been, which, of course, if you are only caring about the synchrotron emission, you can adjust by just pumping up the particle population. You just add more particles to your simulation. But when you go and compute that consistently the inverse Compton emission, the excess particles immediately come out and make you screw up completely your estimate of the inverse Compton emission. Of course, one easy thing to do is to increase sigma, and then you have a nebular field of order 10 to the minus 4 Gauss and can reproduce your inverse Compton emission as well. But at that point, the morphology is completely gone, okay? So in 2D, there was just no way of reproducing at the same time the morphology and the overall emission. The suspicion was that the sigma was too low and was forced to be too low by the excessive buildup of Hooke stresses in the nebula. And in fact, as soon as 3D simulations first made by Oliver Porte and Sergei Komissarov became available, I mean, this thesis turned out to be the right one. So on the right here, you see the flow structure, actually the pressure, a map of the pressure in 2D. And for the same sigma on the left side, you have the 3D representation. You see that the pressure structure changes completely. In 2D, you were building up too much pressure along the axis. Now that you've relaxed the 2D approximation, the magnetic field is free to develop colloidal components to reconnect and alleviate the Hooke stresses in the nebula, so that the pressure distribution becomes more uniform and more spherical. The termination shocks looks pretty much the same in 2 and 3D, but on rather different scales. Okay, it also behaves the same, but on rather different scales. It's much more extended for the same magnetization in 3D. Is 3D solving all problems? Can you then increase your magnetization and reproduce at the same time the morphology and the spectrum of the Crab Nebula? Well, not really. So after Oliver Porte's simulations, we did much longer simulations. Barbara Olmi did them a couple of years later. And here, the subsimilar phase is fully reached. The magnetic field is rearranging and reconnecting inside the nebula at a steady rate. But when you go and look at the morphology and spectrum, not everything is solved yet. In terms of morphology, you can reproduce with sigma of order 1, slightly larger than 1. You can reproduce the size shrinkage with increase in frequency and the sort of wisps that you observe in the radio, but you completely lose the bright torus. There is no bright X-ray torus. And in addition, you're still not there in terms of spectrum. The average field is still too low, and the Crab Nebula spectrum is extremely sensitive to that value. So in these simulations, in order to reproduce the synchronous spectrum, artificial steepening of the particle spectrum and artificial increase of the number of particles was still needed, and the inverse Compton spectrum was still overestimated, even with an injection sigma that on average was 1.5. This means that the Crab Nebula at the termination shock is probably characterized by a sigma which is larger than 1, at least a few. We have a simulation done with sigma equal 3, of which sooner or later we'll we'll look at the results and compute all the diagnostic. Of course, sigma is larger than 1 on average. This does not imply that it's larger than 1 everywhere. This is a side remark that will be useful later. Okay, so far for the sigma determination shock. Then the next step that we tried was to constrain the pulsar multiplicity by studying again the dynamics and the emission of the nebula. What is the issue with the pulsar multiplicity? The issue here is that if you look at this particle spectrum, you immediately see that most of the particles are in the flat part of the spectrum. So these are the ones that dominate the number. These are the ones that determine the multiplicity. So if these particles here are part of the flow and accelerated a determination shock isotropically, what you're forced to deduce is that the multiplicity is high, of order 10 to the 6, and the Lorentz factor of the wind is of order 10 to the 4. Whereas if you, as Kennel and Coroniti did, forget about these particles and focus on the optical X-ray emitting ones, then the multiplicity can be rather lower, over between 10 to the 3 and 10 to the 4, and the wind Lorentz factor correspondingly higher. Okay. So the question is, are radio emitting particles part of the flow? Must they be part of the flow? Well, the answer is not. So we played with our MHD simulations, and we consider different possibilities for the injection of radio emitting particles: injection only at determination shock and advection, or radio emitting particles distributed uniformly in the nebula, which means they've been injected long ago. They were injected long ago, and then they were diffusing and being sort of reaccelerated by turbulence in the nebula all the time. But these are sort of fossil reaccelerated particles uniformly distributed. Well, the radio emission maps are indistinguishable, and even the radio wisps you can reproduce in both scenarios. So even the variability in the inner nebula that you observe at radio frequency, you can reproduce even if the particles are not accelerated at determination shock currently, okay? And this is because actually what the wisps are is they are brightness features varying in time, but they're due to enhancements of the magnetic field. It's like magnetic waves traveling in the plasma that are in this MHD picture making the wisps, okay? So radio emitting particles are not forced to be part of the current pulsar outflow. And so in principle, a low multiplicity and a high Lorentz factor of the wind are allowed. One other thing that you can do by using your simulation is to try and constrain the locations of particle acceleration, okay? How do you do this? Well, exploiting the observations of variability in the inner nebula. We've said we have variable features. We have variable features at radio, at optical, and X-ray frequencies, these wisps. They've been studied with suitable observational campaigns at the same time at different frequencies. For example, here you see data referring to contemporary measurements of variability in the X-rays and in the optical. As I was saying, here these are simulated wisps, and these emission enhancements here result from increased magnetic field, local increase in the magnetic field, and Doppler boosting. Okay, you go and you try to understand whether in an MHD picture you can observe variability that is uncorrelated at different frequencies. If the wisps are only due, as I was just stating, to enhance magnetic field and Doppler boosting, they've got to behave exactly in the same way at all frequencies, right? And this is what you find. So if particles are injected everywhere and you have emitting X-ray and radio and optical emitting particles uniformly accelerated along the termination shock everywhere, the wisps are strictly coincident in MHD simulations. The only way in which you can create misalignment between the wisp variability at different frequencies, if you inject particles in different energy ranges in different places along the termination shock. For example, this picture here corresponds to X-ray emitting particles injected in the equatorial sector of the termination shock and radio emitting particles injected along the polar jet. We tried several different configurations, and the general conclusion of this study was that X-ray emitting particles do need to be accelerated in the equatorial region of the termination shock, whereas radio emitting particles can be accelerated anywhere as long as they are not perfectly superimposed to the locations of X-ray emitting particle acceleration. Okay. So conclusions about this part of the talk concerning what we've learned about the properties of the plasma in the Crab Nebula. Well, from nebular dynamics and high energy emission properties, we've learned that sigma along the termination shock on average must be larger than 1. From modeling the radio emission, we've learned that the magnetization can be low because radio emitting particles do not need to be freshly accelerated at the termination shock right now. From modeling the multi-frequency variability in the inner nebula, we've learned that acceleration of particles in different energy ranges will better occur in different places if the wisp variability has to be reproduced. What are the implications of all this on acceleration mechanisms? Well, first of all, let's see what the possible acceleration mechanisms are. So the three, I think, best studied models are Fermi mechanism, driven magnetic reconnection, and resonance cyclotron absorption in the presence of ions. So the Fermi mechanism, this we all know, I mean, what we're talking about. This is diffusive shock acceleration. This is known to be efficient at unmagnetized electron-positron relativistic shocks. However, it is totally inefficient if the magnetization of the flow is larger than 10 to the minus 3. Okay. And in addition, it is too slow to guarantee the maximum energy observed in Crab. There are ways of making it more efficient, possibly, and this is by including a highly turbulent motion in the shock region. So if you have a highly turbulent, moderately magnetized shock, Fermi acceleration becomes more efficient and even faster. Okay, so moderate magnetization and turbulent flow, I think, is, if one wants to look for the regions in which Fermi acceleration can work, probably the equatorial region of the flow is a place where it can work, and it provides you the right spectrum for the X-ray emitting particles, which in addition seem to be accelerated there based on our study of the variability in the inner nebula. So that might be an important ingredient. Now, it has to be seen whether a sufficiently large fraction of the flow crosses the sufficiently low magnetization region. I mean, quantitatively, I don't think it is assessed that Fermi acceleration can explain everything, or at least all the high energy Crab Nebula emission. Driven magnetic reconnection, you've got these stripes. When these stripes, the stripe Coulomb region, where the stripes are meet the shock, they're compressed, and they will reconnect. However, and magnetic reconnection has the advantage of providing you with very hard spectra in general. So it was long suggested as a possibility to explain the radio emitting particle spectrum. The thing is that there is no way that I can see to make it that consistent in the case of the Crab Nebula. We can maybe discuss this during the discussion. I think this was a very promising way of explaining particle acceleration in the Crab Nebula, but I don't see how it can actually work. Finally, ions. So if you have ions in the wind, the possibility to transfer energy from the ions to the pairs is through resonance cyclotron absorption. Basically, you've got that the ions, as soon as they meet the increased magnetic field at the shock, start gyrating. They leave the equal speed drift that was proper of the wind and start gyrating, and the waves that they emit gyrating can be absorbed resonantly by the pairs, and you can get acceleration up to the maximum energy, up to the ion energy in the wind, which is 2,000 times higher than the pair energy in the wind. Remember, the wind has a unique bulk Lorentz factor. In the case of the crab, numbers tell you that you could get the pairs accelerated up to PeV energies. The kind of spectrum that's provided by this mechanism can be either very hard or very steep, depending on the amount of energy that's in ion. But the important thing is that if ions are not, at least locally, dominating the wind energy flow, this acceleration mechanism simply doesn't work. So it does require the ions not only to be present, but to be energetically dominant, which can only happen if the pulsar multiplicity is not larger than the mass ratio between the ions and pairs. Okay, so kappa cannot be much larger than 2,000. And correspondingly, the wind Lorentz factor cannot be much lower than a few times 10 to the 6. Okay, now there are other suggestions for how the mechanism, for how the acceleration can work in the Crab Nebula. Some of the mechanisms still refer to the termination shock corrugation we already mentioned. It's a way of speeding up. The process is still Fermi process, and I think however, it's sped up with some contribution maybe by magnetic reconnection. Then there is turbulent acceleration at the shock. And again, here we're calling for the effects of magnetic reconnection at some level. An interesting scenario is this proposed by Giacenti and Kirk that assumes that the turbulence level is different at different shock latitudes, and this gives you intrinsically different spectral slopes depending on the latitude. This combined with the information that optical X-ray emitting particles and radio emitting particles should not be accelerated exactly at the same place, sort of makes it a promising route to investigate. And finally, as far as the production of radio spectrum, there is some of very flat spectra. There is some recent work by Commisso and collaborators that suggests that this very flat spectra that we observe in radio emission could not be a result of a flat particle spectrum, but actually a result of the particle anisotropy associated with a much steeper particle spectrum. And the steeper particle spectrum could be accelerated by turbulence. by high sigma turbulence in the nebula. This is an interesting suggestion. I think it should be made more quantitative in terms of where should it happen, what are the requirements in terms of magnetization, what is the maximum achievable energy. But one thing that I want to stress is that, I mean, assuming that there are no particles with a flat spectrum in pulsar wind nebulae, that we're only seeing steep spectra, but at an isotropy level that depends on energy, has very broad implications, because the flat part of the spectrum is exactly what we invoke to explain the excess cosmic ray positrons. Okay, so if those particles are not there with that spectrum, this is a very important thing to to ascertain. Okay, so in extreme synthesis, what have we learned about the possibilities to accelerate particles in the nebula? So Fermi mechanism, we've understood that requires low magnetization. Driven magnetic reconnection requires high magnetization and high plasma multiplicity. Ion cyclotron absorption requires low magnetization, no constraint, low multiplicity, no constraints on the magnetization. If we go back to what we had learned from dynamical modeling of the nebulae, well, essentially the take-home message is that on average, the magnetization at the shock will be too large for Fermi acceleration to work. And even these scenarios in which turbulence is involved, it's not clear to me how large a sigma they can tolerate and still be at work. From modeling of the radio emission, we've understood that the parameter that the radio emitting particles should they are not forced to be part of the flow, which leaves ion cyclotron as a viable alternative. And from modeling multi-frequency emission, we've understood that the radio emitting particles could be accelerated anywhere in the nebula, so they do not impose special requirements on the termination shock. Now we move to the most recent news on the Crab Nebula. The news that come from detection at more than 100 TeV. I don't know whether I should call these ultra high energy or extremely high energy gamma rays. I think we should make an agreement on the subject at some point. But what is the big news? Well, the big news is this Lhasa data points that extended the Crab Nebula spectrum, I think, by almost an order of magnitude in the last year. So we've already said that the highest energy photons was 1.1 PeV, and that this implies that the emitting electrons, if it is interpreted as inverse Compton emission, is 2.4 PeV electrons. This thing here already constrains the average constraint, not the average field, but the field in the acceleration region. Okay, so if you want to accelerate at 2.4 PeV photons, what are the requirements? Well, the zeroth order requirement is that you should have a pulsar with a sufficiently high potential drop. In fact, there is a limit that cannot be exceeded in any pulsar wind nebula that's imposed by the pulsar potential drop. That's the maximum available potential difference. And even at the shock, even through shock acceleration, you cannot exceed that. In the case of the Crab Nebula, this maximum energy is 30 PeV. No matter whether you're talking about protons or electrons, you cannot accelerate particles beyond 30 PeV. Okay. And this I remark because I've seen 100 PeV electrons expected from the Crab. In young energetic systems, however, there is a more strict limit that's imposed by losses. So here you have large magnetic fields and particles lose energy through synchrotron acceleration while they're being accelerated. The fastest acceleration you can conceive, well, So I wrote the acceleration time as E particle energy over potential E, psi, B, and speed of light. And this psi E is the ratio between accelerating electric field and magnetic field, which usually, which in the MHD approximation cannot exceed 1. It can only exceed 1 in the case of course, magnetic reconnection. So if you translate this condition here into an upper limit on the energy, you find this expression here, 6 PV with the field in units of 10 to the minus 4 Gauss. This already sets a limit. As I was saying, the 2.4 PV electron implied by Lahasso emission is telling us that the magnetic field in the acceleration region of these PV electrons cannot exceed 6.5 times 10 to the minus 4 Gauss. Okay, this is an important upper limit, because as we will briefly mention afterwards, basically this magnetic field is lower than implied in the regions from which the Crab flare originate. Okay. Extended SED. So we constrained from the highest energy Lasso photons, we constrain the magnetic field in the acceleration region, but we can also get constrained from modeling the SED on the average magnetic field in the nebula. And modeling on the SED is providing you with this value here of the magnetic field. This is a very nice picture from the Lasso paper, in which from the SED one constrains the average magnetic field within one zone, but still the average magnetic field, the emission energy, and the spectral index. And the best fit magnetic field is 112 microgauss. So in agreement with previous estimate. And the other thing that I think is interesting is that the particle population is in perfect agreement with, say, the aged X-ray emitting particle population, but with a break at 0.76 TeV. So slightly higher than what usually inferred from Crab by other time-dependent modeling. This is not a time-dependent model. This is just a straightforward fit to the instantaneous particle population and emission in the Crab Nebula. I promised I would mention the flare, because that's the other main thing that is providing us constraint on the conditions in the region of particle acceleration. The flare, as I think most of you know, the Crab flares are episodes of high, extreme even increase of the gamma ray flux, in which the Crab Nebula spectrum, which looks like this around the synchrotron cutoff before the inverse Compton kicks in, changes in something like this in the most extreme case. So there is emission that's increased by up to a factor of 30 in the GeV region of photon energies. Now, this emission was an incredible surprise 10 years ago when it was first found, because we were seeing emission beyond the synchrotron cutoff frequency. From this condition here on the maximum energy that you can get from radiation loss limited acceleration, you can immediately estimate maximum frequency of the emission that does not depend on anything, does not depend on the particle energy or magnetic field, but does depend on just the ratio between electric and magnetic field in the acceleration region, and all constants. And this frequency here should not be larger than 230 MeV. So GeV emission was not expected at all. In addition, the variability that was expected was on the month 1.5, well, 2.5 actually, month time scale. for an average field of order 10 to the minus 4 Gauss. Variability just dictated by the acceleration time of the highest energy particles. Instead, in the brightest flare, the flux was seen to double in 8 hours. Okay, this is extreme. And if you want to strictly interpret it as a result of synchrotron emission, even if you have accelerated your particles somewhere else, you need a magnetic field of order 3.5 milligauss and an emission region of size less than 10 to the minus 2 parsec. Okay. How does this constrain the acceleration? The straight answer is, I don't think I know. The suggestion was that this psi e over the 1 was already by itself suggesting magnetic reconnection, the fastest possible, well, the most favorable ratio you can have between electric and magnetic field. I think that the conclusion after several studies, mostly carried out by Benoît Cerruti and his collaborators, I think that the final conclusion was that the rate to 0th order was too low, but maybe you could invoke like explosive magnetic reconnection. All these are things that I mentioned because I would like to have some discussion on them, not because I have a strong opinion on the subject. One interesting recent news about the flare dates back to 2011, but this paper is only 2 years old, is this study here that shows that together with increases of luminosity, there are interesting and relevant depressions of the luminosity. This study by Pshirkov et al. Well, this is somehow suggestive of the possibility to interpret the flares as magnetic field variations in the inner nebula. So you could have a flare due to field enhancement and then a decrease due to field depression, which of course, I mean, if you do this to electrons that are in the cutoff region, if you suddenly increase the field and then decrease it, the consequences are dramatic. I guess that in order to fully reproduce the variability, you should have some additional Doppler boosting, and especially it would be interesting to see whether there are any multi-wavelength signatures that I don't think were discussed in the main paper. Finally, going back to LASO results, the last thing I want to mention is that this increase here, this flattening here at the very highest energy in the LASO band was modeled by the LASO collaboration based on 2 different possibilities: either add a population of thermal or flat spectrum particles emitting in a lower magnetic field, or adding protons. This is something that I cannot help to discuss. This hardening here is actually it could actually be a signature of the presence of high energy protons in the pulsar wind. So the inverse Compton spectrum goes down, and finally you can see the pi0 decay induced by nuclear collisions of the highly relativistic wind protons. Okay, the LASO collaboration proposed 2 different models for the protons that could be responsible for the emission, either a power law or a Dirac delta. This Dirac delta here is exactly what approximately you would expect for the models in which the protons are part of the wind and then they just cross the shock and only gain some sort of a spread rather than actual acceleration at the shock, because they're already at the potential drop. Okay, there is no room for proton acceleration. You can only sort of decelerate them, but based on the old simulations that we were doing of shocks, of electron-positron shocks with protons, they would keep a Dirac delta shape most of the time. Okay, so this is sort of physically motivated for how weird it seems. what you can do if you interpret these data points as due to protons, you can estimate in a straightforward way what is the energy in protons that it requires. And this is over the 3 × 10⁴ erg. So it's very small fraction of the total energy released by the pulsar. And in terms of luminosity, of course, to estimate this, you've got to have an estimate for the escape rate of protons. And the conservative estimate I think you can make is to assume bomb diffusion, since the magnetic field is expected to be mostly perpendicular in the nebula. If you assume bomb diffusion, the escape time is over the 300 here for 10 PeV protons, and you end up with an estimate of the luminosity input into protons by the pulsar, which is only a few % of E dot. Okay. I had asked, actually, even before the LASO data, a PhD student working for the ASTRI collaboration to do this calculation and to simulate the expected high energy spectrum of the Crab Nebula in the presence of protons. Then LASO data points came out and were added to this plot that was made even before the LASO data point, based on basically this work that we did many years ago with Daphne Guetta and Pasquale Blasi. And I had asked him to use different Lorentz factor. There was no prescription informed by LASO for the energy of the emitting protons at the time, using different Wien-Lorentz factors and still reproducing the entire SED, okay? So the Wien-Lorentz factor is in principle a free parameters, but the fraction of pulsar energy that goes into protons is not a free parameter, because the sum of protons plus magnetic field plus positrons and electrons has to match E dot. Okay, that's not a free parameter. When you play the game in this way, what you find is that the best fit for the entire spectrum, including the LASO data point now, gives you a fraction of pulsar wind energy into protons, which is of order 4%. So the end conclusion is that if this all makes sense, this takes into account the time evolution, everything, and the entire SED. So if this calculation is correct, even if protons are there, and even if they're explaining the LASO data point, they cannot be energetically dominant, and they're likely useless from the point of view of acceleration, unless they dominate a tiny shock sector and all that they do is going on there. There have been other studies of trying to constrain the pulsar wind nebula contribution through the cosmic ray flux based on the LASO measurement of the Crab Nebula. And in these studies, the main thing is that a proton spectrum is used, at odds with what we did. Here, a proton on e⁻² spectrum is assumed for the protons, and the diffusion coefficient, the escape, is treated as a free parameter with a diffusion coefficient that's just constrained with the data. In this case, the estimate gives that you can have that LASO data point that are compatible with 50% at most of E dot being input by the pulsar in the nebula in forms of protons, of which only 4% is currently bright, say. My main thing is, can we really reproduce the entire SED from radio to TV gamma rays playing this game? Aren't we like inputting twice as much energy as the pulsar is able to input? Okay, this is all I wanted to say about the Crab. Mostly I was trying to, to launch questions for discussion, because I have more doubts than certainties. Certainties are summarized here, and basically I tried to show you how, based on MHD simulations, one can try to constrain the properties of the flow and understand what mechanisms are possibly at work to explain the wonder of this incredible accelerator that we have at hand. And that's it. Thank you.
Okay, thank you, Elena. So you used 7 minutes more than, so we should decide that last part of your talk, which was the most a bit speculative about hadronic leptonic, it was already discussion. You started discussion with yourself. So, but that is actually is very interesting part, of course. So, okay, let's start. I mean, we skip questions or combine questions with discussion. Please, questions or comments. Okay, there are some. I mean, sorry, I have to look this. I'm using new laptop. I think I'm lost with my laptop. Okay, let's start with Chen Cao. Please, Chen.
So, very nice talk from Elena. But before I make my question to you, I want to inform very sad news. Actually, we have lost our very good scientist, Benedetto Piazzoli di Torre. This is a very sad news. I just got from his nephew yesterday. He passed away on 7th. This is very sad news, and this is a big loss for our community, not only for LASO and also for the whole cosmic ray and the gamma ray. So that's a very unfortunate. Okay. After that, let me make my questions. I have actually two questions. The first one is about the proton part. That's of course is a very, very interesting part as mentioned by Phoenix. So it's really hard to me. I don't quite get the point about this delta function of the energy distribution. Okay. Because those protons seems to be according to your very beginning introduction, and this actually, you know, the protons directly from Pulsar, right? And
from the Pulsar wind.
Yeah, Pulsar went through the everything and out to the acceleration range, eventually produce the photons to us. So it's really hard to understand why the energy is the, you know, it's the only one value.
Because it's so the protons together with the pairs all together move at certain Lorentz factor. That is how a cold wind is formed. So we do know that the pulsar wind is cold before the termination shock. We don't see any synchrotron emission. I was showing these anti-8 regions. We have theoretical, but also observational arguments to assume that the pulsar wind is cold before the termination shock. Are you still seeing my screen, right? So these underluminous regions surrounding the pulsar is hinting at the fact that the wind is cold. A cold wind means a wind that is moving relativistically, but with all particles having very small thermal spread around the bulk Lorentz motion. So there, all the pairs and the protons, if they're there, everything is moving at the wind Lorentz factor, which is gamma. And this is exactly what this Dirac delta function assumes. This Dirac delta, the way I write it, which I'll find here. Okay, this Dirac delta is proton energy equal to MP C squared times wind Lorentz factor, gamma. Yeah. Now, these protons will meet the shock, but at the shock, they're already basically at the maximum energy that shock can provide. So they will start gyrate, but they will gain very little thermal spread around gamma. They will not be accelerated. This is a result also of peak simulations of the systems that we were doing with John Arons in 2006, but before me, Masahiro Hoshino in 92, and after me, Stockham, I don't remember her name because she left astronomy, unfortunately, in 2012. All these simulations of a pair proton wind meeting a shock were showing that the protons were left almost cold by the shock crossing. Cold means that not a power law, just they would gain a thermal spread around a wind-Lorentz factor.
Okay, thank you. My
You're
second
welcome.
question is about the electron assumption. So this electron, if it is electron, and if we have only this part of the proton to explain the really highest part of the energy, is that really helpful to understand the energy is a little bit lower? It's not the 2.4, but something like still very high energy. Is that possible to understand according to the current model?
Flattening. So if it is only electrons, how do you explain a flattening at the highest energy? This is the question.
Yes.
That becomes complicated. I don't really know. I guess that one possibility is that, again, suddenly you're seeing sort of what you're seeing in the Crab flare. You see in the Crab flare what happens is, and we're looking more or less at the same electrons. Okay, this is synchrotron emission, that is inverse Compton emission, but the emitting electrons are the same. In the Crab flare, you see that normally the spectrum is like this, but then you can harden it here, right? And make this bump. The only kind, I mean, since we're not able to explain that, I'm not able to explain that hardening of the electron spectrum, but I guess that some similar mechanisms should be at work. Like, I mean, you're seeing sort of the same electrons.
Okay, thank you.
So, but the thing is that I don't fully understand the Crab flare. So
yeah, but Elena, it could be simply this so-called steady spectrum of the Crab is just simply many flares. So that was dominated.
No, yeah.
So you don't need hardening.
What is making the flare, which is what I still miss.
Yes, but so you need the shift. In fact, you don't need the hardening. So that is how to get the shift is another question. And maybe just I just comment also on these flares and the Lhasa connections. I think is apparently they are not connected, because for flares you need 3 milligauss, so you don't expect much inverse Compton in that case. And
the flares are Doppler boosted, though, I think. So
yes,
I don't know.
But cannot be tremendous Doppler boosted. I mean, maybe factor of 2 Doppler factor, right? 2, 3. Okay, there's a factor of 4, but still, well, that was maybe should not be so confident, but nevertheless, it looks like that it could be separated. So the same electrons, I mean, in one zone, in a very magnetic field, they enter large magnetic field, they are burned. And that case, by the way, if that is the case, you accelerate in a low magnetic field and then produce synchrotron, then you don't have this fundamental limit, this 150 MeV or 200 MeV. So that could be also the reason of the shift. There is a kind of that Biko or others suggested for turbulence, but here is not turbulence, but that's inhomogeneous field, and the stronger one. But what is interesting here, I mean, when we are doing one zone model, of course, there's simplification, but it could be even more fundamental things. Maybe there is at first glance, you see very smooth spectrum. You showed it our almost 30 years old spectrum fitting. But if you look to the details, X-rays are softer and getting soft, and then it should begin harden at the Comptel energies. So recently there's a data, the spectra published by Integral. It's really steeper. So what I want to say, maybe we should really separate. So then life will be easier in modeling, right? You are connected only with X-rays, and then you still could go to very high energies, explain few hundred TeV, and then another component, either protons or electrons, as you mentioned. But the other part, this 100 MeV and above, a synchrotron, it could be simply separated synchrotron component with suppressed inverse Compton component. So somehow I'm saying that could be not one zone is nice, but most likely, even you mentioned multi-zone for other reasons.
No, but I agree. I mean, no, but even, I mean, if you compute the spectrum, this in any multi-D, okay, version of your plasma, even if you inject a single power law, you will always have a spectrum that's not a perfect power law. This is something that I wanted to mention. So here, what we inject are perfect power laws, but then they're subject to losses, which are different depending on the particle paths, etc. Right? So the overall spectrum is not clear that will be a power law in any case, in all places. And there can well be places where there's a sudden bump, or you know what I mean. So in one zone is fine, but of course life is always much more complicated.
But you know, his situation is a bit different, Elena. If you go X-rays, it's really steep. So in order to get MEV part, you make harder spectrum, and that is it's very, very difficult. So two components is much easier to do this job, rather than making intrinsic, the acceleration spectrum to make harder, or to another way. So that was I want to say. It's unnoticed paper, by the way, by Kropp, by the Integral. It's very interesting paper published this year, and I learned about that paper only 2 months ago. And this very, very clear steep spectrum going to hard X-rays. So it looks like situation could be. So in that sense, that these Lhasa results above 100 TeV are the best way, in a sense that it does depend on anything. I mean, just not magnetic field.
Right. Yeah. Yes.
Which is that component independent of anything, and then you could see what will be synchrotron.
Yes, that is the power of going beyond 100 TeV. You're really looking at the particles. It's like with particle detectors.
Exactly. It is.
Yeah, I like that very much. Yes.
Absolutely unique case when you are looking at the particles, electrons,
yes.
or protons.
Yes, in an actual astrophysical source, but you are measuring the particles directly. That's excellent. Yes.
It's really unique stuff. Yeah. So okay, next question, team.
Yeah, thanks for the nice presentation. I have a question to the magnetization sigma. So in the very beginning, you had an equation from Canel-Coroniti, and I believe it was something like the shock velocity over c.
Okay, so from Canel and Coroniti, for the the 1D estimate of the magnetization, yes.
Exactly. So from that, I would think that a magnetization larger than 1 makes no sense.
Right, because this is just 1D. so you don't have degrees of freedom. I mean, if you exceed that value, it's just that you cannot slow down the flow, because a toroidal magnetic field wants to expand at the speed of light, and there's nothing you can do about it. But of course, if your magnetic field is not fully toroidal and your flow is not strictly radial, an entire spectrum of magnetization is on. That's exactly the beauty of moving to multi-D dynamics, that some things are just fake, that are induced by reduced dimensionality. Here, you were estimating such a low sigma based on the fact that you were 1D, and these magnetic loops wanted to expand at the speed of light, and the only way to confine them was to have them underdominant in terms of energy, so that the flow could be confined. Okay, When you move to 1D to 2D, you increase your degree of freedom and you increase your sigma. But the real, but still, I mean, but still in 2D, you are largely underestimating, I think, the sigma. Because again, you're forcing your loops into a cage that that forces the magnetic field to be under dominant. It's just basic dynamics.
Okay, and
I mean,
how
you can
can
see
I?
it like from the very first equation that's written in Canel-Coroniti.
So how can I imagine the quantity sigma? Is it something like the ratio of Poynting flux to particle flux?
Exactly, exactly. That's exactly what it is, right?
Okay. Okay, thank you. And
Right.
I have one more question to the particle populations, which you assume in your model. So you have, say, radio electrons, which are roughly constant over the nebula.
Yeah. So yes, in modeling, in producing these maps here, that's exactly what I'm doing. In this map here, I'm assuming that radio emitting electrons have been produced, I don't know where, but since then they've been scattering in both space and momentum space in the nebula, so as to be now uniformly distributed and with a power law spectrum.
Okay, and then the wind electrons are accelerated at the termination shock.
Yes.
Right, and so do they also diffuse inwards, or do you only have these high energy?
No, it's advection. Advection is dominant in all these MHD simulations. It's just advection.
Okay, but so you only have them outside the termination shock, basically.
Oh yeah. It's not inside. Yes, yeah. No, inside the wind is just cold, and then there are no accelerated particles. No.
Okay, thank you.
You're welcome.
Evgeny.
If you can go back to the picture with the synchrotron bubble, as I understand, there is no big, at least numerically, there is no big problem to calculate the size and the shape of the. I think it was number 12 or something. Yeah. Oh, this one.
Oh, okay. No, this is the Canel-Coroniti. Yeah, it's the same.
Yeah, the size of the termination shock and the shape of the termination shock is something that you can calculate at least numerically. But my question is about the size and the possible shape of the contact discontinuity.
Okay. Sorry, I was in meetings since about 2 o'clock. So are you all right?
Can you hear me?
Yeah. Yes. Now, yes.
Should I repeat?
Yeah. No. I didn't understand the question. Sorry. So you want to know whether I can calculate
the termination shock is kind of evident, but the contact discontinuity depends on the properties of the surrounding medium, which I guess are not very well known. So how certain is the size and the shape of the contact discontinuity?
Oh, you deduce it from, so you've got these beautiful pictures here, right? So here you're seeing the emission of the ejecta. So you estimate the position of the contact discontinuity just from the pictures, and you deduce a nebula radius, which on average is like 1.8 parsec. I think it's like 2.2 and 1.5 depending. So the short radius, I think, is 1.5, and along the major axis is 2.2. It's just, you just estimate it from images in the sky.
So is it correct to say that in fact it's possible that the properties of the material which is emitting is not the same at the termination shock and at the contact discontinuity? So this is coming back to one's own model.
What you're, I mean, In what sense? In the sense that it's not pulsar-produced plasma that you're seeing at the contact discontinuity?
Is it possible that the magnetic field can be really different at the inner part and the outer part?
Oh, yeah,
is
yeah,
it possible
no,
that the particle
is.
distribution will be really different at the inner part and the outer part, and things like that?
So, so you do have spectral index maps, okay, at radio, optical, and X-ray frequencies. And basically, they're consistent. Of course, you've integrated along the line of sight and everything, but they're all consistent with the same kind of particle population in the inner region and in the outer regions, just subject to synchrotron aging. Did I understand? I mean, did I answer your question? So if you go and look at spectral index maps,
more or less, yes.
Yeah. That is like the best diagnostics you can have on this kind of thing. No, on the particle population.
I see. So you, in this sense, your eye is the best instrument. This is what you are saying, right? You just see by eyes, and that's it.
But spectral index is not my eye. No, it's just emissivity in different frequencies. You subtract the map and you get a spectral index map. No, it's just a map of alpha, the slope of the particle distribution that you can get. Of course, you do have the magnetic field, but the magnetic field will be, it's the same. So that is the way to have some diagnostic on the emitting particle population. You look at 4 gigahertz and then at 1.4 gigahertz and subtract the map. And you form these maps that represent the slope of your particle distribution. It's just, I don't know if you call it DI, it's measurement of the radiation, spatially resolved measurements of the radiation in different frequency bands. And these are all consistent with having the same particle population, except that, of course, it ages due to synchrotron losses.
But Evgeny, why you want, I mean, it's clear that could be different magnetic fields. I mean, it could be.
No, but the magnetic field, yeah.
Well,
it's so you want to get a sophisticated way, but
it's mostly the question is not that it could be different. The question is whether we have to say that it must be different or not.
No, for example,
the magnetic field of the particles, maybe.
Kernel current gives you the radial distribution of magnetic field. In fact, at the shock, it's about 30, 50 microgauss, right? And then gets the maximum and slowly. So it's even hydrodynamically in the Kernel coronity, you have variation of magnetic field, radial distribution of the radial distribution of magnetic field.
This is what I mean.
In fact, it's not, it's emitter, it's not accelerator. Particle accelerated, for example, the shock, and then they propagate.
Yeah.
But for example, this is a map. I don't know if you're seeing, this is a map of the magnetic field in the nebula based on 3D simulations. Of course, it's very different from the inner, I mean, inside, closer to the pulsar, and in the outer region, it is very different. Can you see the color map?
Yes.
So this is the sort of magnetic field structure that you get in the nebula. This is magnetic field intensity. And these are the kind of magnetic field lines